good evening. This is Naz from NB Network Lessons. Hope everyone's doing okay and in high spirits. My today's topic of discussion is to find energy stored in a capacitor. So I have set it up for you. This is basically the initial design where you have two capacitors connected in series. 2 microfarad, 8 microfarad, all right? T at 0. At the time 0, the voltage V1, which is right here, is minus 10 volt. Voltage T2, which is right here, is minus 5 volt. And the current at time greater than 0 is I sub t is equal to 240 e raised to the minus 10t microamperes. Okay. So then what we do is that, if you recall from our last lecture, what we can do is we can find the C equivalent, right? And I showed you we can find C equivalent like this. C equivalent, actually this right here is going to be 1 over C equivalent. Fix that real quick. 1 over C equivalent, okay, is equal to 1 over 2 microfarad plus 1 over 8 microfarad, and when you solve this you get 1.6 microfarad. So then 1.6 microfarad is my equivalent capacitor, which I have it right here, basically the same diagram, and we have terminal A, terminal B, and then equivalent microfarad. Now we want to find out what's the energy stored in this capacitor with respect to time. Okay, so let me just kind of warn you that finding C equivalent does not really always deliver the right answer. What I would like to do is I would like to solve this and prove it to you, okay? And then I will, in my next lecture or lecture after, I'll show you how we can find the correct way to find the energy stored in capacitors. Now, there's another thing. Before I get started, I would like to review real quick integration because we're going to use that integration, and I don't want you to get lost because I might be skipping some steps. So I don't want you to be confused at how we got that and how did we get this number and so forth. So basically, let's review integration real quick. So let's say function of t is equal to, we're gonna use definite integral 0 to t e minus 10t dt. How would you solve this? Because we're going to use this, okay, we're going to use this when we are solving this problem right here. So basically we do this by substitution. We say, let's say u is equal to minus 10t, okay? Then we say du, okay, over dt would be just minus 10, right? I'm taking derivative of both sides. Then we can say dt is equal to 1 over negative 10 times du. Now let's go back to this and plug in. So function of time is equal to 0 to t e, we replace minus 10t by u dt. Now finding integral of this should be piece of cake. So what we do is that we say if we find integral of this, then basically what we have is let me see, eu dt. So then, as you know, I solved dt, which is equal to 1 over minus 10 du, so I can plug that in, 0 to t eu, just replacing this dt by this value. So times 1 over negative 10 times du. Easy peasy, okay? No rocket science over here. This is Negative 1 over 10 is a constant. We can pull it out of the integral. So then we have 0 to t, negative 1 over 10 EU du. Now solving this should not be hard at all. So then what we do is that we say, okay, negative 1 over 10 times EU, as you recall from my previous lectures, Euler's rule, this e raised to the power u is indestructible. You cannot, if you take derivative of this or you take integral of this, it remains same. So then the EU plus, we always have the constant. Okay, so then basically we substitute the value of u back. So then negative 1 over 10 times e raised to the power minus 10t plus c. This, my friends, is the answer. Okay, so I'm going to come back and solve the energy problem and in the capacitors, and then we'll go from there. Okay, but I just kind of wanted to bring this up and revise your integral because we're going to use this and I don't want you to be confused when I'm solving this. Thank you so much for watching. Hope you liked it. If you do, go ahead and give me a like. Thank you.